All right. So last class, we look at the binary search in a sorted array. Okay. In particular, if you are given a set of numbers, want to search for a specific one, then we show that if the array is already sorted, then we can do it using the so-called binary search operation and do this very efficiently in time log n, versus if you do a linear search, that's linear time. Log n is much faster than linear time. Okay. Of course, that this requires that our input array is already sorted in non-decreasing order or non-increasing order, okay, from small to large, for example. Okay, and this is the topic of today. This is the sorting problem. In other words, we're given a set of numbers, an arbitrary set of numbers, array of numbers, and we want to convert them into a sorted array where all the elements are ordered from small to large. Okay, so this is called a non-decreasing order. You can also do from large to small, but in this class, unless I otherwise specify, we are going to assume that a sorted array is in from small to large. Okay, just by convention, it doesn't matter either way, it's fine. Okay, so that's the problem, the so-called sorting problem that we're going to look at today. Okay. All right, so sorting in some sense is by far one of the most well-studied problem and used very commonly in many applications. And there are many reasons why we want to solve the sorting problem. Okay, it could be that, let's say that we're given a list of tasks with different priority importance value. Okay, and what you want to do, your CPU may want to process them from importance to less importance. You want to solve those with high importance first. In this case, you want to sort the array based their priority score from large to small, okay? Or as we will see, in fact, we already saw last time, sorting sometimes can make other problems easier. So for example, if we want to do a search for, to do a search query in a database, like what we discussed last time, by spending some time to first sort all the elements in the database by their keys, then we can perform binary search and then do the search query much more efficiently. Okay, and so there are different reasons why we want to sort an array. Okay, so in this class, we're going to focus on the simplest version of the sorting. Okay, which is that you're just given a list of real numbers stored in an array, and we want to sort them small to large. But there's more other variants of this to handle different type of data and so on. Okay, and for example, in databases, sometimes you want to do range queries in multi-dimensional databases, not just the one key anymore intuitively. There are multiple ones. Okay, in that case, we want to it's no longer just sorting a list of numbers. We actually want to have a multi-dimensional data structure to handle that. Okay. All right. So let's start with, let me just hold on for a second and close the window. Sorry about it. Okay, let's start with this first very simple algorithm for sorting. That's a so-called selection sort, which many of you may have seen before. Okay, so the idea is very simple. Okay, we're given a list of numbers, an array of numbers. Okay, like in this example, we have this here. What we want to do is that I'm going to, at each iteration, one by one, I'm going to identify the smallest number currently in the remainder unsorted portion of the array. And I put it as the smallest one at the end of the portion that's already sorted. Basically, I keep getting the smallest for the part I haven't sorted yet, and then arrange them in order. Then in the end, I get a list of sorted number from small to large. Okay, so just look at this example. What do I mean? Well, in the first iteration, so I'm going to maintain a pointer. So this pointer, here maintains where we are. The portion to the left of it is basically already sorted, and to the right it is not yet sorted. Okay, at the beginning we have nothing sorted, so the pointer is here. Okay, and then what we do is that in this unsorted portion, we identify the smallest one. So we look through it, we find the smallest number. In this case, the smallest number is -1. So what we do is that we say, okay, let's now put this one first, okay? And the remainder, by putting this one first, I can swap it with the first one. So then the remainder I have, this is a current array, okay? And then now this portion is already sorted. So this is already sorted and this is not yet sorted. Okay, then I repeat. I say that, okay, what is the smallest one now? Well, now the smallest one is 4, which is already the first. So we don't need to do anything. We basically swap it with itself. We added it to the portion already sorted, namely, I move this pointer indicates this always, let me write it here. The pointer, whatever to the left of it, it's always the portion that's already sorted. Right is the part we haven't yet sorted, okay? Then next, I look at the remainder portion. Now it's only 3 numbers. I identify the smallest one. In this case, it's 9. So we say that, okay, now I replace the 9 with the current. Put the 9 in the end of the portion already sorted. That means I'm going to have -4, -1, 4, 9. So I swap 9 and the 12, and the 12 and 10. So now the pointer moves here. So this is already sorted. Remainder is not sorted. Next, I identify 10 is the smallest, so I have. Okay, I have only 1 element left. I don't need to do anything anymore because I know that must be the smallest in the remainder because there's only 1 element left. Okay, so in the end, as you can see, we have a sorted array. And the idea is that very natural. You want to sort them from small to large. You basically keep finding the smallest among the remaining number and then put the next and assemble a new array from small to large. Okay, so that is the algorithm. Okay, all right. Now, the idea is very simple. How do we implement this idea? How do we write the code for this idea? Implement this using an algorithm. Okay, and naturally you can write the your algorithm, but then you have to prove that it's correct. Okay, at least convince yourself that it's correct, and also how do we analyze the time complex of the simple approach. Okay, so let's go through that one by one. Okay. The way that we're going to implement this idea is that we're going to use an algorithm called in-place sorting. What does in-place mean? This just means that you start with an input, which is the input array, contains all the numbers. Like before, it was -1, 12, -1, and so on. Okay, in place means that the algorithm is going to operate on the same array. We only need at most a constant number of extra pointers or memory variables to help us, but then we don't need to open a new array. We're just going to manipulate the current array. Okay, it's called in-place sorting. Okay, and the idea we described earlier, if you remember, we keep finding the smallest in the portion that we have not yet sorted. So for that, we need a pointer to help us to separate the good portion, which is the array, which was part of it, which we already sorted to its left, and the remainder, the unsorted portion. Okay, so that is going to be a pointer, which we call it a barrier ID. Okay, this is the barrier between separating the good, the parts we already sorted, we keep getting smallest and arrange it, and then the remainder. Okay, all right. And here is the algorithm. Okay, so the algorithm is called selection sort. Okay, naturally because we keep selecting the smallest, and the barrier ID, this separation goes from 0 to n-1. Okay, you can think that everything smaller than the barrier ID, that's a portion we already sorted. So at the beginning, the barrier ID, we put it to be 0. So like in the previous case, at the beginning, the barrier ID is 0. Okay, because to its left, that's a portion we have not yet sorted. Okay, what do we do? Inside, we first find the index of the portion of the array starting from barrier ID to its right, namely all the unsorted portion, okay? Because from the array A starting from the barrier ID to n minus 1, that's basically the portion we have not yet sorted, okay? So we find the smallest one. And then we do a swap. This is just that we swap. In this case, let's say this min ID is actually 2. Okay, then we swap what's here with the current barrier ID because we put that into the front. Okay, so that's what we do. Then after that, we move up the barrier ID by 1 to the next, and so on, and then repeat. Okay, so this is exactly the procedure we described earlier. Okay, all right. Now, of course, here to find the minimum, I'm calling another procedure. As we said, this procedure simply find the smallest. So this is what we have here. This procedure find the index of the minimum from the portion of the array within the range from the start ID to the length of it, okay, till the end. Okay, and finding minimum, we are very familiar with it now. At the beginning of the class, we also talk about finding maximum. This is just a symmetric version. All you need to do is that you just go through every element one by one and always maintain the smallest one. You use min value to maintain the smallest one you've seen so far. Okay, all right, so that's the this procedure. Note that obviously, I didn't have to write this in a different separate procedure. I could have the previous algorithm. We could have this algorithm, and instead of writing this procedure here, I could write that inner for loop there to find the minimum of the remainder portion. Okay, so in other words, this algorithm can be written just using a nested loop here. Okay, all right, so that's a complete algorithm. Following this selection sort, where we repeatedly find the smallest elements, select the smallest element of the remainder, and then put it in the sorted portion at the end of the sorted portion. That's it. Okay. All right. Correctness. So how do we convince ourselves that this algorithm is correct? Again, it might by design, the way that how we had this idea of selection sort and the right converting it to the algorithm, you may already be pretty convinced that this is a correct. Okay, but let's just go through the process a little bit more formally once again. So here, very often when you have an algorithm, you are given a piece of code that you didn't design and you are supposed to show that it is correct. What do you do? Okay, so in this algorithm we just seen, it has a loop or sometimes nested loop. Okay, and the way to prove that this is correct is using something called the loop invariants. Okay, and it's a little bit similar to the inductive idea we mentioned last time to show that the recursive algorithm works. Okay, in particular, what is the loop invariant? Well, a loop invariant is a statement that holds that is true at the end of each, that you argue that is true at the end of each iteration of your for loop. Okay, so it's an invariant, namely something that holds for each iteration of your loop. Okay, and now what you want to do is the following. Okay, you want to show that this loop invariant holds at the beginning, basically for the base case. Okay, at the beginning you show that it holds, and then you argue that, okay, if it holds at the end of the i-1 iteration, then you argue then it also holds at the ith iteration. Okay, if it holds at the i-1 iteration, then it holds at the end of the ith iteration as well. Okay, once you can prove this, so this is the inductive step. Okay, so this is base case. So once you prove that, how does the argument work? Basically, it holds at the first iteration. Then because of that, it holds at the second iteration. And then because of the inductive step, that means it holds at the third iteration, fourth iteration, and so on. You apply the inductive step repeatedly till you reach the last step. So in the end, what you want to argue is that if your loop invariant is designed right, if you choose the right loop invariant, then when at the end of the algorithm, you argue that the loop invariant implies that the algorithm is correct. Okay, so that's usually the procedure. Okay, so let's look at the more concrete example of this algorithm to see what I mean. Okay, just to remind you, so this is the algorithm we had, the selection sort. Okay, and we have a for loop here. Okay, intuitively, how did the for loop comes? Intuitively, our algorithm basically runs by at every moment. We pick we already sorted some portions, okay, and then we're going to find the smallest of the remainder and then put it there, okay? So if you think about it, what properties does the algorithm have at the ith iteration after we run this for loop I times, okay? So after a bit of thinking, you realize that really here is what we can guarantee, what the algorithm is trying to do. Okay, so this is the loop invariant that we're going to claim for the selection sort. So we're going to say that the selection sort has this loop invariant. Okay, so what is the loop invariant? We said that after k iterations, okay, then the first k numbers in your array A are already sorted. That's number one. Okay, number two, not only that, they are also smaller than all the remainder n minus k numbers. Okay, intuitively, this is a case because that we repeatedly take the smallest one by one and then put them into, rearrange them in the array. So whatever we take out, those are all the smallest possible. Okay, so all the things we didn't take out, the remainder portion are going to be bigger than the first k numbers. Okay, and in our code, in our algorithm, because of the array starts with index 0, okay, so this our barrier ID, okay, the equal to k minus 1. In other words, the iteration number k here is our barrier ID plus 1. So when we start in the first iteration, the barrier ID was 0, okay, because the indices in the in Python for the array. Okay. All right, so this is the loop invariant we're going to claim that the algorithm has. Why is this a good loop invariant? Well, we note that if this loop invariant holds for any iteration ID k, okay, then what does it mean after k equal to n minus 1 iteration, where n is the length of your array? Okay, what does it mean? That means that after n minus 1 iteration, the first n minus 1 numbers are already sorted, okay? The last one, and we also know that the first n minus 1 numbers are smaller than or equal to the last one. In other words, the last one left has to be the largest. That means that all these n numbers are sorted, okay? So we see that if this loop invariant holds for every iteration, then after k equal to n minus 1 iterations, this loop invariant implies that our algorithm returns us a sorted array at that moment. Okay, so intuitively, the algorithm every time the algorithm would add one more sorted element to the first k numbers in the array, and these are the first k smallest numbers. Okay, all right. So what remains? So we convince ourselves this is a good loop invariant to satisfy our intuition and also would imply the correctness of the algorithm. Okay, so what remains is just to prove that this loop invariant indeed holds. Okay, and as we said, the way to prove that is that you start from the base case, say that at the beginning it holds, and argue that after every iteration it still holds. That's it. Okay, so this now, the base case is basically at the beginning, before we even start any iteration. Let's say that's called a zeroth iteration, okay? So in that case, iteration ID is k equal to 0. Of course, at this point, we basically, the loop invariant says that the first k number are sorted. Now, if k is 0, of course, they're sorted, and because it's empty. And then everything, all the remainder ones are bigger than this one. So clearly it holds at the base case for k equal to 0. Okay, the next step to prove this is the inductive step. You show that if this loop invariant holds for iteration k minus 1's iteration, okay, then it should, after we now perform the case iteration, at the end of the case iteration, it also holds for the case iteration. That's what we want to prove. Okay, so if it holds for k minus 1's iteration, okay, what does it mean? That means that at the beginning of the k minus 1's iteration, let's say that we already processed this for a while, okay? So after k minus 1, so let's say that after k minus 1 iteration, you have k minus 1 number here, okay? By our assumption, we assume that the loop invariant holds for k-1 iteration. That means that all the elements here are smaller than all the elements here. Okay, so it could be that 1, 4, 5. And what you have here is not necessarily sorted, it can be 8, 7, 9, 6. But then they're all bigger than what's the first k-1 iteration. Okay, remember, what does the algorithm do? The algorithm says, okay, in the case iteration, we first find the smallest one among this unsorted portion. In this case, that's 6. Okay, then we move 6 to the portion to after the to the beginning of this unsorted portion. In other words, after that, this is what the already sorted one. Now we move 6 here, say by swapping with us 8. Then after this, obviously, what remains, because this is the smallest one in the remainder, so then after we move 6 to the front, what remains here are still bigger than everything in the to the left of 6. Okay, 6 and to the left. In other words, the first k number now are all smaller than the remainder. Okay. Furthermore, this portion is already sorted and they're all smaller than what's here. So that means the 6 is bigger than anybody in this shaded region. So that means that afterwards, the first k numbers are all sorted. Okay, because I'm just adding another number that's bigger than what's here. Okay, so by design of our algorithm, the loop invariant now holds after this case iteration. It holds for the for iteration k, namely the first k numbers now also already sorted and they're smaller than any of the remainder ones. Okay, all right. So what we just described is that we showed that this loop invariant, we showed that it holds for the base case. Okay, then we showed that the inductive step says that if it holds for k-1 iteration, then it holds for k iteration. So now apply this inductive step one by one from k, because it holds for k equal to 0 by the inductive step. That means that k equal to 1 step after 1 iteration is also good. Also, the loop invariant still holds. Then apply this again. That means that after 2 steps, loop invariant still holds. And you repeatedly apply till we have k equal to n-1, and using the inductive step, all of them, the loop invariant must hold. Okay, and we also said earlier that if the loop invariant holds after n-1 iterations, that means that all the first n-1 numbers are sorted already, and the last one has to be the largest. That means the entire array now is sorted. So then we get to that. Because of this loop invariant, we have that algorithm. The final output of the algorithm is a sorted array from small to large. Okay, so that's how we use this to prove. All right. All right. Now, in general, when you are given the algorithm and ask you to prove its correctness, and if it has 4 loops, and when you want to use the this loop invariant idea, usually the hardest part is to figure out is to find the correct loop invariant. Okay, so for this example, for this selection sort, if I have a different loop invariant, if I say that, okay, the loop invariance at iteration k means that the first k numbers are the small are sorted. Okay, this is also a correct loop invariant. But this loop invariant, after you prove it for all iterations, it does not yet imply that the algorithm will give you a sorted array. Okay, so what I'm saying that even though that is correct for each after each iteration, but just using this loop invariant, you cannot really prove the inductive step actually. Okay, that's why in the end you couldn't use it to prove the correctness of the algorithm. Okay, so finding the right loop invariant is often the key in using loop invariants to prove the correctness of an algorithm. Okay. On the other hand, if you think about it, the idea is quite natural. What the idea is, what this loop invariant is saying is that to prove something is correct, you think that the algorithm is working in stages. At any moment, it solves a partial problem. And your loop invariant is basically trying to articulate what is that a partial problem it's solving, okay? And what you want to argue is that as this iteration increases, the problem gets bigger and bigger, and in the end, you solve the complete problem, okay? In this particular case, we keep finding the case smallest number, put it in the beginning. That's what this partial problem we're solving, okay? All right. Okay, now the time complexity of this algorithm. Well, this algorithm essentially, in fact, let's go look at the algorithm again. This essentially is okay. So at the beginning of the algorithm, this just takes constant time, okay? Then we have a for loop, okay? Now, inside the for loop though, we have this command, this line, this is calling yet another procedure. Okay, so you need to first figure out how much time does this procedure subroutine take. Okay, and this is also taking only constant time. So the key is to figure out how much time does finding minimum take. Okay, now finding minimum, what we did. So here, this subroutine is looking for the smallest number among the portion of the array from start to the length of the array, to the end, say n minus 1, right? So, and the way the algorithm, we just saw the algorithm, what it does is that it just look at every element inside and then keep remembering the smallest one you've seen so far. And in the end, you return the one smallest you've seen so far. That's the smallest of the entire portion. Okay, so basically I have to visit every element within this subarray. Okay, that means that we need to take time linear to the size of this subarray. Okay, what does it mean? That means that it takes time. This subroutine takes time big theta of the size of the array minus this start. Oops. Okay, so that's the time it takes. Okay, now what does that mean? Well, oops. I'm sorry, I'm not familiar with this iPad, and now I couldn't shrink my screen. Okay, so now what is the time complexity? Well, in the first iteration, when barrier ID equal to 0, then this step, this find minimum, take time, C times m minus 0. Then when barrier ID equal to 1, then this takes time. Remember, this takes time proportional to m minus the size of the subarray you are checking. Okay, so now the size, you only check everything to the right of the barrier ID. So as barrier ID increase, the size you're checking is getting smaller. Then as barrier ID goes to m minus 1, then we check C times n minus m minus 1 equal to C times 1. Okay, what is the total cost? The total cost is the sum of all of them, which means that the total cost of this algorithm becomes Cm plus Cm minus 1 plus Cm minus 2 plus, because this is the time it takes for the first iteration, time it takes for the second iteration, third iteration, and so on. Okay, and altogether, this gives us Cm plus m minus 1 plus 1. But this is just the arithmetic series in the opposite order. Okay, so what we have is C times 1 plus 2 plus 3, which is order of C squared. So this is a quadratic time algorithm. Okay. All right. So this is what I wrote here as well. That's the time complexity of this algorithm. And all right, so let me